All right. Good evening, everyone. We are recording now. Are there any questions regarding what we did last time? Did everybody see how exactly we got to the dual of the linear program? And we also proved the weak duality theorem for standard equality form linear programs. Right. So the main idea was you have a maximization LP, in particular it is in standard equality form. So for a maximization LP, you want to establish upper bounds. So if you think about it this way, and then you use this plan of considering linear combinations of the constraints, right? So if you go through this derivation, you would yourself be able to figure out what conditions you really need, right? So here is the main derivation. Right? So if you want an upper bound, you want to subtract something from a certain quantity. And that something, if it is a non-negative quantity, then you will have an upper bound which will be equal to Y transpose B. And the way to get a non-negative quantity is to just look at what does your X bar look like. Your X bar is non-negative, therefore this vector should also be non-negative. And if you go through this process for any linear program, you would be able to come up with a duality theorem for that particular form of linear program. So in particular for the standard equality form, the dual looks like this. So you have a maximized C transpose X subject to AX equals B, X at least X is non-negative. So your dual is going to be minimize B transpose Y subject to A transpose Y is at least C and Y's are free variables. Okay. All right. Did anybody write down the dual of this linear program? Right. So here you have a minimization problem. So your dual would be a maximization problem. And what do the constraints look like? Does anybody have any idea? Okay, if not, that's fine. Probably you didn't try it. We are going to do something more general today, so I'm not going to write it down right now. You can write it down based on today's discussion in case you didn't think about it from the last lecture. Okay. So today I want to talk about a couple of things. Let's see how far we get. So we have seen weak duality for standard equality form LPs. I want to show you how to write the dual of any linear program. And I also want to talk about certain cool consequences of weak duality and strong duality. We'll also write down the strong duality theorem rigorously, right? So let's see, where should we start? I want to start with one quick consequence and then we will go to writing the dual, okay? So one quick consequence that I forgot to mention explicitly last time is a certificate of optimality. You might remember in the last module, we talked about certificates of infeasibility and unboundedness, right? We didn't talk about certificate of optimality because it is very closely tied to duality. And so I did not want to repeat too many things, okay? So if you remember how we discussed duality last time, we started discussing it as deriving upper bounds on the value of any feasible solution, right? And what we noticed is that whenever we have a vector that satisfies this condition here, which we rewrote as A transpose Y is at least C, right? That will give us some upper bound. And in particular, if you want to convince someone that a certain X bar is an optimal solution, what you want is that the upper bound has exactly the same value as the value of X bar, right? Which basically means that your Y is an optimal solution for the dual. So if you have such an x bar and a y bar, then you know for sure that the x bar is optimal for the primal LP, and also you know that the y bar is optimal for the dual LP. So such an x bar will be such a x bar y bar pair will be your certificate of optimality, right? So let's just write this down. So what is our primal? It's maximize C transpose X subject to AX equals B, X at least 0. And the dual that we wrote down is minimize B transpose Y subject to A transpose Y. And there is a C over here. And can someone tell me what the sign is?
Greater than or equal to.
Greater than equal to, exactly. And these Y's are free variables, right? So for a linear program in standard equality form, your certificate of optimality will simply be an X bar, which is a feasible solution, and a Y bar. Y bar should be a feasible solution to the dual. So that means that it should satisfy A transpose Y, at least C. And what's the other condition we need to make sure that these are optimal solutions?
The value of C transpose X should be B transpose Y.
Exactly. B transpose Y bar is equal to C transpose X bar, right? And so this is exactly what acts as a certificate of optimality, right? So if I covered it back then in module 3, it would be a bit too mysterious. So it's better to just see it in the lens of duality for a standard equality form LP. Okay. So yeah, so certificate of optimality is extremely closely tied with duality. All right. Does everybody see why such an X bar and a Y bar classify as a certificate of optimality for the primal program? And of course, this is also a certificate of optimality for the dual. And we are thinking of everything from the point of view of the primal, but of course you can switch their roles, and now you can think everything from the point of view of the dual, and this is still a certificate of optimality for the dual linear program. All right. So if there are no questions regarding this, we will return to duality and its consequences in some time. But before that, I want to talk about writing the dual of any linear program. Okay. All right. So let's see. So let's say you have a primal linear program, which is a maximize or minimize C transpose X. So let me put a question mark here. Subject to AX equals B, AX question mark B and X question mark 0. So the way I want you to think about it is, this is your bunch of constraints, right? Each row in the matrix A corresponds to one constraint, and the right hand side would be the entries in the vector B, right? And what I want you to think is, some of these could be less than equal to, some of them could be equal to, some of them could be greater than. Okay. So we will actually write down, if you like, we can write down a vector of less than equal to, and greater than equal to. We'll also see a concrete example. And when I say X question mark 0, I want you to think of it the same way. Some of them would be less than equal to, some of them will be greater than equal to, and some of them will be free variables. Okay, so I'm going to abuse notation, and I can say x free 0 to mean x is a free variable. Okay, so there's some abuse of notation here. Okay. So my dual will always be, you will have some minimize or maximize B transpose Y subject to, and now we'll take A transpose Y question mark C. Notice that B and C, they flip roles, and you will have Y question mark 0. Okay. All right. So we know what to do. If we know that, oh, this is a linear program in standard equality form, we know what these question marks stand for, and we can write down the dual. What I now want to do is, I want to tell you how to write down the dual of any arbitrary linear program. Okay. So think of the P being given to you, and the D is what we need to figure out. Okay. Okay, so the first thing, there are some things which are very easy. So the first point, maybe you can tell me. So supposing the primal is a maximization problem, what should the dual be? Or if the primal is a minimization problem, what should the dual be? Opposite of the opposite. Okay, good. So let's just put that down. So if this is a maximization problem, then the dual is going to be a minimization problem. And if this is minimization, then the dual will be a maximization problem. Okay, that seems clear. Max becomes min, and min becomes max. In fact, I'll put arrows in both ways. Why not? All right. Can anybody tell me why were the y's in the last lecture? Why were they free variables? Why did we not consider y greater than equal to 0 or y less than equal to 0?
We initially started with y as just factors, multiplying factors for the equations.
Right.
So there we cannot just so it's basically just doing row operations. So we don't have any constant on y.
Right, exactly. Basically, the main point is those are equations. So because they are equations, you can multiply them by whatever y you like, positive, negative, and they will still hold. If they were inequalities, then you would have to be careful. Okay, so the point is, okay, maybe I should say another thing before we get into this. Let me also write down one concrete example. I want to have some space over here. Okay, we will figure out. Let me just put down a concrete example on the right hand side here. Okay, I think it will help to have one concrete example. So let's think of the following. Let's say the primal is maximize 3, 5, 10 x subject to 4, 1, 0, 3, 4, 3, 0, 1, 7, 2, 0, 1 x, and I'm going to put a bunch of different signs here. And my vector on the right hand side is 1, 8, 2, 1. Okay, and I have x1 is a free variable, x2 is non-negative, and x3 is non-positive. Okay, this is my primal linear program. We need to figure out what the dual is. but I will write down what we already know. So the dual, we already discussed that if the primal is maximization, the dual is a minimization problem. So minimize 1821 times a vector y subject to transpose this matrix. So what do we get? 410, 343, 017, 201. We get a y here. We get some constraints. We don't know what they are. We are still going to figure that out. And we get the objective function in the previous one was 3, 5, 10. So we get 3, 5, 10 over here. And we need to figure out the variables y1, y2, y3, y4, whether they are. So I will not write them down. I'll just say, okay, y1, y2, y3, and y4. Okay. Okay. So before we go into the details, I want to point out one observation in case you haven't noticed it. So remember, what did we do in our derivation of the dual last time, or when we were trying to discover the dual linear program? We were multiplying each constraint by a certain number, right? So the first constraint we multiplied by y1, the second one we multiplied by y2, y3, and y4. So notice that for each constraint in your primal, you have a variable in the dual. When I say constraint here, I'm not referring to non-positivity and non-negativity constraints. I'm just referring to the constraints in AX question mark B. Okay. So for every constraint of the primal, you have a variable of the dual, which makes sense because you are transposing the matrix, right? And similarly, for every constraint in the dual, you basically have a variable of the primal. So that's how you want to think about it. The first constraint in the primal corresponds to the variable y1, which is called a dual variable. And similarly, the first constraint in the dual corresponds to the variable x1, which is a primal variable. Okay, so the constraints and variables sort of correspond to each other in that sense. Okay, maybe I'll just write it down here. Primal variables are in correspondence with dual constraints, and likewise dual variables are in correspondence with primal constraints, right? And here when we say constraints, we are excluding the greater than equal to 0 and less than equal to 0 constraints on the variables, right? So those are separate. Does that make sense? And if I am not mistaken, what Varun just said is that in the last lecture, all our y variables were free variables because all the constraints were equality constraints, because it was a standard equality form linear program, right? So it was AX equals B. Okay. So now can anybody tell me in the dual, which variables will be free? So I have 4 variables, y1, y2, y3, y4. Which of these should be free variables? Sorry?
Y3 can be free.
Y3, exactly. That's exactly what happens. Y3 becomes a free variable. Okay, so that's, let me just write that down in red color. So y3 is a free variable. Okay. And which of the constraints in the dual will become equality constraints? The dual has 3 constraints corresponding to the first row, the second row, and third row of this matrix. Can someone tell me which of those constraints will become an equality constraint? Should it be the first or the second or the third?
Sir, I may be wrong, but I feel none of them should become equality because we can't just leave out inequalities.
Um,
I don't know how to frame it properly, but somehow my intuition is not able to go ahead.
okay, fine. Anyone else? There is going to be an equality constraint. But what I want you, so you want to think of primal and dual interchangeably. Remember, when you had an equality constraint in the primal, the corresponding variable in the dual became a free variable. So now, if you think about primal and dual interchangeably, what should it suggest? There are three variables in the primal, x1, x2, and x3. x1 is a free variable, x2 is a non-negative variable, and x3 is a non-positive variable. So which one of these three should become an equality constraint?
Oh, x1 should now become an equality.
Exactly.
Okay.
Right? So if a free variable, right, if equality constraints correspond to free variables, then in the same sense, your free variables will now correspond to equality constraints. Okay. So that is the next thing that is easy to remember. So equality constraints correspond to free variables. And I won't write it down again, right? I mean, and free variables correspond to equality constraints, right? So that says everything you need to know. All right. And is there anything else? All right. So those are the easy things. And now we need to figure out the rest. Okay. So here is what I plan to do now. I don't want to go into the math of it, right? I mean, the math of it is the same as what we did last time. The only difference is that now we have a much more complex linear program. So if you go through the arithmetic, you can figure out how the correspondences should work out. What I'm going to instead focus on is just a simple memorization technique. So that if you have a primal linear program, you can just immediately write down the dual linear program. Okay? And I hope that the arithmetic of it is something you can figure out yourself by going through what we did last time. Okay? That is if you really want to, as far as the course is concerned, when we come to combinatorial optimization, we will not have such wild linear programs. Our linear programs will be much more well behaved. If you remember minimum cost perfect matching or shortest path, all the constraints were either greater than equal to, or less than equal to. And the variables were one of the three possibilities, right? So as far as the course is concerned, like applying to combinatorial optimization, we won't need to write linear duals of wild linear programs. But at the same time, this is something I want you to learn from the course. So given any linear program, I want you to be able to write down the dual of that linear program without having to go through the whole arithmetic every single time. Right? All right, so what I want to tell you about is a simple memorization technique that I learned from a colleague of mine when I was in my PhD. And it is based on the idea of what are called natural constraints and natural variables. Okay, so I'll tell you what this is. Natural and unnatural variables and constraints. Okay, so I'll tell you what natural variables and natural constraints are, and though the other ones are going to be unnatural. All right, so let's talk about variables. Right, so what we now need to do, we already know equality and free and everything. We just need to figure out the greater than equal to, less than equal to constraints, and the variables, which ones are greater than equal to 0 and which ones are less than equal to 0. Okay, good. So let me erase this red circle here. Okay. So we will say that a variable is natural if it is non-negative. So for variables, always the non-negative variables are going to be natural variables. Okay? Natural variables for any linear program are exactly the non-negative variables. Okay? It's just a memorization technique. All right? And I want to tell you which constraints are natural, but this depends on whether your problem is a maximization problem or a minimization problem. Okay? So for a maximization problem, the natural variables, let me ask you the following question. Maximize x1 subject to x1 less than equal to 5. Another possibility is maximize x1 subject to x1 greater than equal to 5. Which one do you think should be natural? It is very intuitive. Can someone tell me which of these seems to be natural?
Less than or equal to.
Sorry?
The less than or equal to 1.
Less than or equal to. For a maximization problem, less than equal to is natural constraint. So the natural constraints for a maximization problem are less than equal to, and the other constraints are going to be unnatural. Oh, sorry. Greater than equal to. Okay? And for a minimization problem, it is going to be exactly the opposite. The natural constraints are going to be greater than equal to, and unnatural constraints are the less than equal to constraints. Okay? And now the rule of thumb that can help you to write the dual of any linear program is that natural constraints should correspond to natural variables, and similarly natural variables should become natural constraints. Okay? So natural variables correspond to natural constraints, and therefore it follows that unnatural variables correspond to unnatural constraints. Okay? Sounds like a lot of blah blah blah. It will become clear once we do this example. So now I want you all to remember just this much, right? Just remember what is a natural constraint and what is not a natural constraint. For variables, it's very easy. Natural just means non-negative. Non-positive is unnatural, which kind of intuitively makes sense. Okay? So now I want to figure out what should this constraint be, the second constraint. So the second constraint in the dual corresponds to the second variable in the primal, which is x2 greater than equal to 0. So that variable is non-negative. Therefore, it is a natural variable. So in my dual is a minimization problem. So what should be my natural constraint? Right? So what should I write down here? X2 is greater than equal to 0, so it is a natural variable, which means it is a right. So it should correspond to a natural constraint in the dual. The dual is a minimization problem. So what are the natural constraints in the minimization problem? right? It's a greater than equal to. You all agree? Can someone tell me what about the third constraint? So what should the third constraint be in the dual? Should it be an equal to? Should it be a greater than equal to? Should it be a less than equal
Less than equal.
to? Less than equal to, right? What did you look at? Can you briefly tell your thought process?
Like x3 is unnatural, so
Exactly. So you look at an unnatural constraint, right? Thank you. Okay, good. So we have all the constraints of the dual figured out. Now we need to look at the variables. So shall we begin? Let's look at y1. Y1, should it be a non-negative variable or should it be a non-positive variable?
It should be a non-positive variable.
Non-positive, exactly. And what about the other two variables, y2 and y4?
They should be non-negative.
Exactly. Okay, that's it. All right, so this technique works for writing the dual of any linear program, right? Of course, we started with the maximization and you wrote down a minimization dual, but you should also be able to do the same thing following the exact same rules, right? So if your primal is a minimization problem, you would follow the same technique and figure out what the dual is. The dual in that case will be maximization problem. Okay. I also have a written note about this. I'll share that with you too, in case you don't remember it or whatever. Okay. All right. So this is how you write the dual of any linear program. Right? So anytime in life you are faced with writing the dual, I hope that this course will at least um, help you in writing down the dual of any arbitrary linear program. All right. So yeah, so as far as I said, in this course, we are not going to be that concerned with arbitrary linear programs because we are going to look at specific combinatorial optimization problems. And so you will have some structure in the linear program. It won't have all kinds of constraints and all kinds of variables. So when it comes to proving theorems, weak duality, strong duality, etc., we are going to focus on certain special forms like the standard equality form, etc. Okay. All right. Maybe I should state the general weak duality theorem. Right. So now at this point, we know how to write down the dual for any linear program. Right. And that brings us to a general weak duality theorem that applies to all linear programs. So this is theorem 4.1 in the text. So it is weak duality general case. So let P and D be a primal dual pair of LPs. Right? So it's standard to use P for the primal and D for the dual in general. And let us adjust notation so that P is a maximization problem. And therefore D will be a minimization problem. And let X bar and Y bar be feasible solutions with respect to the primal and the dual respectively. Okay. So always the value of x bar will be less than equal to the value of y bar, right? So in particular, C transpose x bar is less than equal to B transpose y bar if we are using the standard notation. Right? And secondly, if they are equal, so it's exactly the same thing as we wrote last time, but now instead of standard equality form LP, we are focusing on any kind of linear program. If equality holds, then x bar and y bar are optimal solutions with respect to the primal and the dual. Okay, so we proved weak duality for standard equality form LPs, and on your assignment you might be proving weak duality for other special cases using a very similar thought process. We won't prove the weak duality for the general case because we are not going to use the general case, and largely it is just technicality. So now rather than dealing with one kind of constraint, you have to do the arithmetic to deal with all three kinds of constraints. So you have to separate your constraints into less than equal to, and greater than equal to. And for each type of constraint, you need to use the corresponding type of variable, right? So as far as the mathematical ideas are concerned, there is nothing too deep about it, right? The depth is already covered in the standard equality form LPs, right? So it's merely a matter of figuring out some elaborate notation and making sure that the right variables are multiplied with the right constraints. Okay, so there is nothing deep about this proof. That's why we are going to skip it. Okay, so omitted, but similar in spirit to special cases such as standard equality form LPs. Right. Okay, so that's that. What else? We also did a concrete example. All right, so now I want to talk about some other consequences of duality, and we'll also talk about strong duality in that. All right, so here is I want to actually write down a table. Let's say you have a primal LP and a dual LP. Okay, you know that any linear program is going to be one of three possibilities. Either it is infeasible, or it has an optimal solution, or it is unbounded. So let's put down all these possibilities. So when I say optimal, I mean it has an optimal solution, and unbounded is the last possibility. And similarly for the dual, it is either infeasible, or it has an optimal solution, or it is unbounded. Right? So I want everybody to be able to distinguish between weak and strong duality. I think it's important to know when exactly you are using weak duality and when you are using strong duality. Okay. So what I want to do is I want to figure out if all of these possibilities can actually happen. So is it actually possible that let's take one particular example. Is it possible that your primal is unbounded and your dual has an optimal solution? Can the primal LP, let's think about the primal being a maximization problem, right? So the dual is a minimization problem. So could it be that the primal is unbounded and the dual has an optimal solution? Okay, why?
The primal solution can get arbitrarily high.
Right.
So, and then that is a lower bound for the dual.
Right. Okay, in other words, if there was a dual solution, it would serve as an upper bound on the primal. Is that right?
Yes.
Right. So if the dual, so you can think about the dual as a minimization problem for the sake of convenience. So if the dual is a minimization problem, if you find a feasible solution to the dual, that y bar, the B transpose y bar, will now be an upper bound on your primal's optimal solution, right? So if you have an upper bound, how can the primal be unbounded? It can't, right? Okay. So this situation can never arise. No means not possible. And that is by weak duality. Can someone tell me, is there another box here that is an impossible situation to arise?
So since this whatever table is being is formed will be symmetric, this optimal unbounded also will not be possible.
Right.
Primal being
So
optimal and
this
given
is also not possible. Yeah. In fact, if one of them is unbounded, then what can you say about the other?
Infeasible.
One of them is infeasible.
it
If
has
one
to
of
be
them is,
unbounded.
think about it again. If one of them is unbounded, the other one will be unbounded or will it be infeasible?
Infeasible on this one.
Infeasible, right? Both of them cannot be unbounded. If one of them is unbounded, that means the other one can never have a feasible solution, because if the other one has a feasible solution, that will place an upper bound or a lower bound on the other one, depending on maximization or minimization, right? Okay, so that means you can not only not have an optimal solution, you cannot even have a feasible solution, because every feasible solution will give you an upper bound or a lower bound respectively for maximization and minimization problems. So if one of them is unbounded, the other one has to be infeasible. So this is also not possible. And therefore, this is always a yes. So if one of them is unbounded, the other one has to be infeasible. And likewise, if this one is unbounded, then this one has to be infeasible. Okay. All right. So these are all consequences of weak duality. Okay. So we have filled up some parts of this table based on weak duality. We will come back to this table when we think about strong duality. Okay. So here in this table, yes means possible, no means not possible. And this means weak duality. And later we will come to strong duality. Okay. So I just want to write down a corollary, summarizing some of the things we discussed. So this is corollary 4.2. So as usual, P and D is a primal dual pair. We won't say which one is maximization, which one is minimization. It turns out it doesn't matter. So if P is unbounded, then the dual is necessarily infeasible. And likewise, if the dual is unbounded, then the primal is infeasible. And finally, if okay, one more point. Supposing both of them have feasible solutions, then what can you say using weak duality? Supposing the primal and the dual are both feasible, right? I want you to think about the number line, right? So think about the primal as a maximization problem and the dual as a minimization problem for the sake of convenience. So let's say both of them have a feasible solution. So there is x bar and its value is something, right? This is C transpose x bar. And the dual has a feasible solution y bar and its value is B transpose y bar. So by weak duality, not using strong duality, what can you say about both of these linear programs? Right, so I'm assuming that if P and D are both feasible, then what can I conclude? Can I conclude that either of them is unbounded? No, right? Because if one of them is unbounded, the other one is infeasible. So they both can't be unbounded. They both can't be infeasible because we're already assuming they are feasible. So what can you say now?
They both have as optimal solution.
They both have optimal solutions. Then P and D both have optimal solutions. The reason I am emphasizing on this point is I want you to realize that by weak duality, you cannot conclude that the maximum value of the primal will be equal to the minimum value achieved by the dual. Right? So you cannot conclude. It is possible by weak duality in theory that the primal's best value is somewhere here and the dual's best value is somewhere here and there is a gap here. Strong duality says that this gap does not exist. This gap is zero. Okay? So I'm going to make a clear point about that here. We cannot conclude using weak duality that the optimal values of P and D are equal. In theory, there could be a gap. If we just use weak duality, right? But strong duality says that gap does not exist. Okay, that's
Sir,
why
I had
yeah, go ahead.
one question related to this. So
Yeah.
when we were doing auxiliary LPs, there also we were talking something very similar that said, okay, if I have an LP, I can formulate an auxiliary LP, and based on that, I will decide the feasibility or infeasibility of the original one. So
Right.
is this related to the primal dual problem anyway?
Not really. There we were really forming a different LP. I mean, we were forming a LP which is very closely related to the given LP, right? But it's not the dual or anything. What was similar there, I mean, I can give you some connection. You might recall that we discussed certificate of infeasibility over there.
Yes.
And what happened was that the certificate of infeasibility that we got from the two-phase method, give me a second. Sorry. Right. So how did we get the certificate of infeasibility? We got the certificate of infeasibility by looking at the auxiliary LP, and the auxiliary LP, the optimal value was not zero, right? It was less than zero.
It was
So
less than zero.
what we did is we actually took the certificate of optimality for the auxiliary LP.
Okay.
And we used that. That is exactly the certificate of infeasibility for the original LP. So there is some connection, but no, the auxiliary LP is not directly related to the dual. It is, in a sense, it is different, completely different.
Okay, I got that.
But yeah, I can see why you would think that there are some similarities in what we are discussing. All right, good. So these are some consequences. maybe I'll state one more theorem. Actually, you know what? Yeah, so I'll just state the strong duality theorem finally. So there are two versions. Let me just state one version today, and we will conclude the lecture at that point. So let's say P and D, as usual, is a primal dual pair. Right? And what strong duality says is that if there exists an optimal solution x bar for the primal, then there exists an optimal solution y bar of the dual, and furthermore the values will actually be equal. Value of x bar in P, so generally our C transpose x bar, will be equal to the value of y bar in the dual. So basically C transpose x bar is equal to B transpose y bar using the usual notations. Okay, and we won't prove strong duality in general again for all kinds of LPs. We will prove it for linear programs in standard equality form. And there is a way to prove it for all LPs by first converting to standard equality form and then proving it for that. But we will focus on particular forms. So we will prove this only for, and we will rely on the termination of the simplex method. Okay, so yeah, so that's I think all for today. We will continue our discussion tomorrow. I'll give you one more version of strong duality, which is equivalent to this version, and then we will proceed to proving this, proving the strong duality theorem either tomorrow or on Friday. Okay, good. So that's all for today. I'm here for another 10 minutes if there are any questions or concerns. All right, so I'll stop recording now.